So basically, this is the the OBINexus derivative tracing system, which is just what I call verified calculus. But it's a derivative tracing system. It's my implementation of token specification, but it just traces derivatives like, I would want to trace like the next step on trace is really like if you have like a series of derivatives, or like some kind of series of I want you guys to go about myself now. So because a series of derivatives you can trace the thing with a particular sequence, like sequence is like a repeating pattern that happens in sequence, and a series is like it repeats over and over again. Series like a series of execution, like a series of steps you can trace. A series is something that's recurring. But something one of them is infinite. I think it's the series of something. Yes, sequence. The sequence like cuts off and joins again, but it's like a pattern that repeats. But it can be the set, like a property set. And so basically, my idea was to like have this measure derivative set, then have like a series function, like a series that OTT series to go up and down, but it's which is also a sequence. But you can identify whatever the problem is, and then you have to put in a framework of whether it's infinite or not. If it's not infinite, you then have to class some derivative problems based on the P versus NP clarification problems. Like this is a derivative in the polynomial space, non-deterministic polynomial. Problems that are easy to solve, easy hard to solve. Which is the next step forward? Let's get into this. So basically, the OBINexus derivative system. This is verified calculus. Is it actually checkable? Can you check it? Does it work on the internet? Can you verify it? Okay, next. The hidden risks. Oh, okay. Meeting ODTS. Oh, why is this going forward? Okay, I don't really know. No, it's going so fast. So no, it's going so fast. No, basically, you have to pause this somehow. So basically, oh, I don't know. Okay, this is the hidden risks of the hidden risks. How do I pause this? So basically, you can get the slide too, but I don't. I want to know what the button pauses and no. Pause. Basically, it's going. I don't know what's going on. Wait, wait. One second. Let me pause it first. Let me pause the recording. I'll be back. Let me pause this recording. It's going too fast. Pause recording. Why is it still going? Okay, pause. I'm not stopping this presentation. I'm just pause recording. It doesn't allow me to pause file. Sorry, I'm still going. It's just weird because it's like, am I going too fast? Okay, so basically, we gotta start again. So this is the hidden risks. So basically, we got the ODTS. The hidden risks is like, so this is a derivative system. It's meant to be paused. So basically, here we are. So this is where we are. Oh no. Why is it not pausing? I have to start again. Oh, this is okay. Sorry, I'm not making a new video after this. It's like a shit video I'm making now. Okay, okay. No. So this is a derivative system from master mission. Critical assurance. So this is a framework for traceable, verify, order-ready derivative in safety critical systems. So you can really trace the derivative, whether you're having like a spaceship or something, or like something going really in orbit, outer orbit. Orbits. Or like orbits around the Earth. You have to maintain an orbit, like a satellite, human satellite. Where humans can go. The thing is, framework really works by ensuring that the calculus you're doing is verifiable. If you don't know, people that take the space shuttle don't go all the way up. They use the curve of the church of the Earth to get to use that trajectory, because when you throw a ball, it's meant to curve around the Earth, and they're meant to curve in. around the Earth, so they don't really use all the speed to go up and stay in orbit. They go at an angle to catch the orbit, and they get chucked around the orbit to catch. Because you know that if you go in an orbit, you don't need to go past the orbit to come down to the orbit. This can verify that and do it perfectly every time. If you do your maths right. But you know, the thing about orbit is like a polynomial formula, and you can check whether you are using the right trajectory. The right trajectory at infinitely. You go into orbit, you go in, and then you can get to the state of orbit where you don't have to put any changes off, and you don't need to use any power anymore. You can stay in orbit for indefinitely. You don't really need to do it if you get to the sweet spot. You know, which you can find in an atmosphere basically. Next one. When one derivative fails, okay. Basically, oh no, let's do it again. No. Okay, so I'll go back and do it again. Oh no, guys, no. Okay, so I'll do it here. Go next. Okay, so basically, when the one derivative fails in the single mass. Okay, basically in that. Any example the thing can when the derivative fails, it's like a list control favor. Yes, so basically a drawn 5 part is governed by polynomials. A bug in association a 2-second derivative can make a stable or cause a crash. Rex, how do you prove each derivative in a model is current and terminates? But you know, we want answers, but we want proof. But you know, you can verify the sequence. If you have the goal is not infinite duration anyway. It's like, you know, a system that remain coherent. But you know, after new updates, new hardware, new robotic systems, the system must be rigorous to do itself, prove itself. But you know, the goal is to verify the proof. Really to go beyond the proof, verify each stage of repetition and optimal reduction of isometric derivative problems. Like you know the cats, traditional cats. Okay, yes, that's the other one. The cats. No, guys, there's another one. That's all. But you know, you don't prove you prove every duration to model into elements. So, determination is very cool because you know that handling a case where there's an edge case as an infinite derivative to compute, and there's no solution. There's no solution. Only one solution, or two or more solution, or many one or two solutions. Two or many solutions. But you know, because you have to have the right solution as well for that problem. Whether it's one or two. But that's what I'm saying is like, do you know the solution of the derivative is correct? Are you sure that this derivative, when this drone flight by the polynomials doesn't crash when it comes to a new something you didn't encounter in the specification? How do you prove each derivative is like there is no proof in traditional models because you can't, because you know we only got answers, we only got like the answers, and that's a problem because if you think of the sequence of a series of problems, you know you have like a my one actually does I say go d1, d equals 1, d equals 2, but if there's like a d equals 3 and we're working on with the second derivative, sorry, but you know the problem is in the first derivative, and you get a problem that you don't check with this framework, you then get an out of bounds that's caused by the second derivative coming to the first derivative. Based on some model, then you don't really yes, it reduces the problem. But you know that's what I'm saying. So you see like a drone is flying and you get something, he encounters like a second derivative problem. But that problem is a second derivative problem that hasn't been reduced to a first derivative, and it doesn't think about it thinks in a first derivative mode. So it tries to just like be linear, but it doesn't know how to compute that problem because it's ambiguous. It doesn't know. It just does the job. So the second derivative is like a cap on it to deliver the derivative, and it just does the thing with the derivative. So the second derivative is very important. So you got the second derivative, which is like curvature. It's kind of instead of curving, it just doesn't know the problem because it isn't under the problem. Only the answer wasn't there for that problem, but there's no proof. So you have to like have the way to resolve the DAG in this one. So you got like so you're gonna know, I'm still on second derivative, I'm still on first derivative. Now I have no problem. Now I'm just okay. Now I'm looking the first derivative and second derivative. Not no problem. But that's what my framework does. It tracks the states. But the growers have like a series and sequence of equations, derivatives that you know to solve. The Google can be all the problems in that domain, all of them, because the program has to track it and do them over again. Mr. ODTS, so let me just pause it here. So basically, a framework that transfers calculators from traceable variable. Okay, so trace systematic calculation of derivative d1, d2, or the trail. Verify guarantees polynomials like many times, exhausts zero, flags non-termination, cross check for consistency. You can cross check and record each step in a repairable log, provided my helpful for certification review. Basically got this one now. Oh, still pause. So we got order-based tracing. The tracing application engine. So I just read this. I read this. So basically, this one just means like you trace it, you verify it, and you audit it. You check whether it's correct. You replay it because that's like key part of it. You trace it, you check which is correct, and you audit. You can go at any step, but it should repeat really. The original tracing. The tracing application engine. So basically, so you have like the tracing engine, which is like the auto-based system market. Order can be sequences or series of location. D1, but order of derivatives it really matters. How you do it, a series education, how you. I'm thinking of a direction, a cyclic graph structure. So there's no edge case involved. It's a loop. It's a closed loop. That you don't have to handle new cases unless you are tampering with the system. Based on K, infinite and K principles, like how system does it, and you got termination checking, which is like for integrated program with n+1. So basically, things that doesn't really account for multiple zero. So basically, anything that's 1 plus ahead multiple zero, must be to solve that problem. Like it's not like an edge case, like something that you don't. Based on quality social measures, true, positive, true, negative, false, positive, it flags an error, and then he makes partial derivatives for okay. Schwartz theorem, basically partial derivatives are like a multivariable calculus. But these when you have a one variable in one system, you can run a variable to give the system because there's just something you have to know because it's all polynomials. You involve many terms, but you don't know all the terms to solve because it don't give you all the terms. That's what it is. So partial derivatives are just multivariable calculus equation that you solve over polynomials. It reminds me of Horner rule, but this is Schwartz theorem. But this is what Schwartz theorem is in my view. That's what I'm saying. The cross verification of calculus derivatives like a dy plus dx plus dx1 0. But there's multiple missing multiple variables in the equation, which is really known as a partial differential equation because there's more to solve and there's on many unknowns, more many unknowns. Okay, more to solve like more to get to bit by bit sequence. Okay. Level 3 0. So basically, verify a polynomial model. So this is a polynomial, which like many times, the weighted trace is like st. A function s takes the property t equals 3t cubed plus 2t squared plus 7t plus 5. d1 is velocity. So we got like, if we can do right anyway. So basically, you have to draw on paper. I can't remember how to do it. Okay, let me try to do it myself here. So ODTS. So we got a function st equals 3t plus 2t 3 plus 7t plus 5. So we got the d1 equals 9t. Because we gotta do bring down the number to a constant. So 5 basically the 5 becomes 0. Since it's 5 to the power 1 equals 5 minus 1 0. 5 okay, so basically 5 to the power 0. So bring the reverse root 0 is 0. So 5 to the power of 0. 5 to the power of 1 is 0. Minus 1. Because now minus 1 0. So basically that's 0. So basically 70, that's 70 t to the power of 1 is 70 to the power of 1. So that's d1. I'm trying to call it d1, d2, etc. So 7, as you get 70, 70 t to the power of 1 is 70 to the power of 1 is 7. So we got like minus 1, 0. That's like 370. But you know, it's like so but this is just something good. So like it's meant to be velocity, acceleration, jerk, or collapse. But the invariants, like you know, jerk will be like the jerking, but the collapse can be D3 can check for jerk and collapse. Based on inverse kinematic. You think of K is kinematics, the jerk of something can be jerking in an inverse kinematic sense. If it doesn't jerk, it's like control collapse. It doesn't. It's like I'm gonna slow down to get to a goal because I don't want to spot it, doesn't it? But jerk is crucial to solve a problem too. But like more control. Okay, so we got if the derivative is 0, so we got like so 3. Okay, and let me just start from the right to the left. So we got 3t. The d1, the 3 squared, 3 minus 1 minus 2 minus 1 equals 2. 3 squared. 3 squared is 18. 18t minus 3 minus 1. 2 minus 1. So basically, I'm thinking like 3 squared minus 1. You know, this is, let me get this check it correct, please, man. Because 3 squared minus 1 is 18. 18 minus t squared minus 1. T squared minus 1. So basically, d1, so basically t, you got a t2, you got a t2, and then you got t2, because t, we're gonna minus 1 from the derivative. Minus 1 squared, minus 1 from t, minus 3 minus 1 is 2. And 2 minus 3 squared is 9. So with 9 squared 2, and that's d1 equals 9 squared 2. D equals 1, and then 2 squared 2t2 will be 2 will be 4 times 2, because you know we've got 2 squared t cubed minus 1 is t. We're gonna t minus 1 will become 3 minus 1 again will become 2 minus 2. 2 minus 1 will become 1. That'll be 1t, and that'll be the other one will be 3 times 1. I mean, because you know you got 2 times 2. So bring down the 0. Okay, square root and minus 1 from it. So basically, you square it and you minus 1 from it. So like so basically do 2 squared is 4, and you know 4 minus 1 is 40, and that'll be 7 to the power of 1 is 7. 7 minus 1 is 0t. So that'll be 8 and 5 is just 0. Remove that, so that's d1, and then d equals 2 will be the same thing for d1, and then 9 squared is what? 18. 18 minus 1 is 18t, and this is d2. And then t will just be 4, because you know 4 minus 1, 4 times 1 is 1, and then d3 will be d equals 3 will be 18, and then 18 plus 18 plus, I'm just trying to check this out, 18, and then d4 equals 0. So basically the summation of this stuff is d4, and that's 0, and this is 0. Basically 0 just means like, so we just worked out again, but you know the same thing I got, but it's like but you know for partial derivative equation, things like that, you have to have like what I'm talking about, like if it's like a partial derivative equation, I'm thinking of a series of equations, like you know if the system encounters this state and this state and this state, you want me to go this state and this, and there'll be a DAG, like you know versus like a circle, get like a D1 to D2 to D3 to D4, and that'll be like the resolve state. But like a state machine model, like a computational model as a Silicon Valley, because you're gonna model as a state machine to, but you're gonna solve it. You're gonna be able to like solve it itself. But it's more of a state machine diagram, like a automaton, like a hybrid direction instruction automaton. Which is like formalized as basically. Which I've also found is an active system, but like not a passive system, like an active system for AI. Which means like based on a consumer observer model and AI sensors. But the goal is for this to be communal to know what it's doing. If this can use some case structure, like the system must react to the record that is processing for real world use cases too. Especially in like ocean depths, at ocean depths, or in space, they're not really useful. And then we've got this one, multivariable calculus proof. Okay, so basically, this is gonna pause anything. But what I'm saying is finding. So basically, this is f of x equals s cubed minus equals 3x. But this is gradient, the curve, like the gradient, like the refers to the So this is multivariable, but it's like a matrix. Because this is a multivariability gradient. But we have a gradient which is like, but let's just change of x, f of the function f